Okay, so welcome everybody. I'm Nikhil Srivastav. I'm a senior scientist here at the Simons Institute. Welcome to the Simons Institute. Let me say a few words about it. So it's an institute for collaborative research in theoretical computer science, which was established by a very generous grant from the Simons Foundation in 2012, and they continue to support us. And the goal of the institute is to explore algorithmic thinking, both in computer science and also in neighboring fields, such as natural sciences, social sciences, even, and so on. And the way this is done is mainly by organizing semester-long thematic programs in which we bring people together, experts from all over the world, young researchers, to explore some topic. And this program, Complexity in Linear Algebra, it's aligned with the mission of the Institute. It's an outward-looking program that seeks to engage with the math and applied math communities. The program is organized by me, J.M. Landsberg, Olga Holtz, Oded Schwartz, Peter Bergesser, and Daniel Kressner. Where's Daniel Kressner? Okay. Well, he should be here soon. Let me say a few words about logistics. We have coffee breaks with snacks and coffee between the talks, as you see. We don't provide lunch, and we encourage you to go outside and explore some of the restaurants around for lunch. If you want to leave your stuff when you go for lunch, there are lockers on that side of the building where you can leave your stuff. And please don't bring food in here. So this is remarkably clean for an auditorium that's been going on for this many years, and so don't do that. If you're active on social media, please consider sharing your impressions. And finally, I want to give a big thanks to Francis Klingenberger and Ashley Hassan, who did all the work of arranging the logistics for this workshop. So please give them a hand. Okay, so now I'm going to put on my other hat, which is as an organizer of this program, and say a little bit about the program. So this program is about the basic problems, computational problems of linear algebra, namely matrix multiplication, solving systems of linear equations, and solving eigenvalue problems. And what this program does is brings together people from three different kind of scientific cultures to study these problems. And those are, theoretical computer science, and then something I'm going to call pure math, whatever that is, and then something I'm going to call applied math.
It's very broad. Numerical linear algebra.
So I'll say, so it's okay. So this, maybe we know what this is. This is people who do worst case analysis and care about N. This includes all kinds of things like random matrix theory, algebraic geometry, commutative algebra. This includes in particular numerical analysis, I will say, although there's of course interaction between these things. And what's interesting here is even if you look at a simple problem like matrix multiplication, if you're from these different cultures, you'll see different things. If you're from math, to you this is probably a question about the rank of a tensor. If you're from numerical analysis, you might ask different questions about precision, numerical stability, communication involved in an algorithm. If you're from theoretical computer science, you might even ask something like, well, how is the complexity of this related to the complexity of this? And how can we speed this up with randomization? Is there a way to do this approximately? And so these are completely different types of questions. And so there's an opportunity here. We have very different perspectives on these important questions. And there has historically been a lot of progress from exchange between these different areas. So for example, sketching is an idea which mathematically originated in functional analysis, made its way to theoretical computer science, and then was combined with preconditioning in numerical analysis to get some really good algorithms which actually work. another idea that was influential was smooth analysis. It was developed in computer science, became a highly influential topic in random matrix theory, which led to all kinds of developments there, and then came back to these fields and has had algorithmic consequences here. Matrix multiplication, recently there has been progress using tools from algebraic geometry and commutative algebra, which appear to be quite distant fields. So there is a record of progress, but often it's taken years for these ideas to move between these fields. And that's because there are real challenges. There are also lots of failures of communication, miscommunication, thinking that what other people are doing is kind of nonsense. And so that's why this format I'm very excited about this format that we have, as far as I know, the first time for a whole semester, people from all of these groups to try to make progress, but also really set a foundation for lasting conversation for years. That's the hope. That's for the program. Anybody want to add something? Yes, Jim.
Don't forget the computer architects.
Computer architects, yes. So there, you're right. There's also high performance computing. There's a whole part of computer science outside theoretical computer science. and those are people who actually compute things on computers. So and there's an adjacent program on algorithmic foundations for emerging computer technologies, which is about hardware. And we hope to have engagement with them as well, because of course in the end, design of libraries and things like that depends on hardware. Okay, that's all I want to say about the program. Anybody want to add anything about the program at large? Okay, so I'll hand it over to J.M. Landsberg to talk about the boot camp.
Yep, I'm already wired. Yeah, so there's 3 components. My mic's a little loud, I think. The tutorials, so if you're an expert on matrix multiplication and you're not bored in my talk, I have failed. These are supposed to be for non-experts. And even more so, you sit through a talk, there's something that's bothering you, you think it's stupid. It's probably not, and we actually set aside time for you to ask those kind of questions, those very naive questions, and we want you to feel comfortable doing so. We also, for each talk, will have homework, and there will be time in working groups to go over those homework problems. I would encourage you to go to a working group, something outside your expertise, so you can learn about something new. We have all semester to try and solve open problems. I don't think this is the week for that. I think this is the week to try to establish communication between these different groups. Okay. So I think Peter's going to chair the session.
Everybody, I understand the idea is that the organizers introduce us very shortly. So my name is Peter Bergisser. I'm from Technical University of Berlin. I started.
Take a mic.
Yeah, okay. That better?
The other one.
This one working?
You need to switch it on.
Okay. Now. Okay, then maybe I start all over. So my name is Peter Bergisser. I'm from Technical University of Berlin. I did a lot of work in algebraic complexity here when I was young. And then I moved on to more numerical computations, geometric complexity theory, et cetera. So I'm really one of, I really care about connecting these different areas. It's dear to my heart. Otherwise, I don't think I have much to say what J.M. described about the setting of the boot camp. The idea is to have a lot of interaction. And I think that's all I have to say at the moment. So, Olga, do you want to say something?
Oh, that's okay.
Yeah.
We have J.M. to listen.
Aha. I thought the organizers present themselves, or is it?
If you like.
Yeah. Let me say something, but you are a local anyway.
Okay, hi, I'm Olga Holtz, who actually got the ball running on this program, so blame me if something goes wrong. And I am mostly interested in these interactions between different fields, such as numerical analysis and classical linear algebra, you can call it core linear algebra, abstract algebra even. So I'm curious about tensors. I know very little at this point, but I hope to learn more with J.M.'s help. And yeah, I'd love to talk to everybody here and explore things.
Okay. Oded?
Hi, I'm Oded. I have a theoretical computer science education, but then back in 2008, thanks to Jim and Olga, I learned about high-performance computing and trying to connect theory to practice, mainly in the context of matrix multiplication. So looking forward to work here.
Okay, so we've actually ended the remarks early, so we have 3 minutes. So maybe we should take, does anybody want to say why they came here and what they would like to get out of this boot camp? Come on, people probably came here for, I mean, some people are already here, but like.
We should ask the author of linear algebra done right.
Okay.
Sorry for putting you on the spot.
Hi, I'm Sheldon Axler, as Olga said, the author of the book Linear Algebra Done Right. And I came here because I know linear algebra well, but I wanted to learn a little bit more about the other topic, complexity theory.
Okay. Anybody else want to comment? Okay, well, I'll just say a little bit more about the exercises. So JM, so this is really meant to be like a pedagogical exercise this week, and so many of the lectures have exercises, and we've posted the exercises on the workshop webpage. There's a PDF that might be updated lightly over the week, and so. In the past, this has worked very well. People say they actually learn something by doing some exercises, and in the working groups, that is what we will. That is the plan for the working groups, to actually be doing some of these exercises. Okay, well, we're basically. I think we're basically at time. So, Peter, you're chairing the session.
Okay, so it's my pleasure to introduce JM. Actually, he doesn't need an introduction. He just introduced himself, and so he will he will give the first tutorial on tensors and its relations to other parts that are of interest for this program. So please, JM.
Okay, well, thank you. No, I'm wired. Okay, so I guess I should say a little bit about my background. I'm theoretically trained in differential geometry, representation theory, and algebraic geometry. And it's only because of Peter that I began working in complexity theory. So you can credit or blame him as needed.
Same here.
All right, so like I said, if you're an expert, you're supposed to be bored. So let's begin at the beginning. So let's see, a matrix M, we'll say, has rank 1 if it can be written as a column vector times a row vector. So let's write my column vector, say x1 to xa times some y1 up to yb. And I want to distinguish column vectors from row vectors, and I'm going to be like the quantum people and give my vector spaces names. So if the vector space has dimension little a, I'll call it capital A. And to distinguish row vectors from a column vector, I'll just put a star here. So formally, if we were working without coordinates, this would be the space of linear maps from the vector space B to our ground field. In this talk, the ground field will be whatever you want, but it's probably better to take the complex numbers because all polynomials have roots there. And everything, other fields I don't understand so well. And so if I call this thing x and I call this thing beta, I'm going to use notation for this matrix M. I'm going to write it as X tensor beta. And if the rank of M equals 1, then the matrix vector product say V maps to M times V is cheap. Why? Because this M is just X beta, and this is really just going to be beta evaluated on V times the vector X. And similarly, if M has low rank, say M is some, okay, let me put over once. Say if R is much less than the dimensions of the vector space, this is still cheap. And we could use the rank of a linear map as a measure of its complexity.
So there's some reason you have arrows on X but not on beta?
Well, it's because I did a notational crime here. If I call this Y1 up to YA, then I don't need the arrows. I don't like to use one symbol for two different things, especially at the beginning of a talk. I should be consistent, so thank you. Right, so we should really think of M as a linear map from the vector space B to the vector space A. And let's let A tensor B star be the space of such. And given a linear map from B to A, we could also, so M in A tensor B star, can also think of M as a bilinear form. So this is like complex numbers or real numbers, your favorite field, which for me is the complex numbers. Although, yeah, so this would be just some alpha B would go to alpha MB. Each two vectors spits out a number, linear in each factor. Any questions? Yeah.
I guess you mean at most low rank R.
Thank you. Any non-expert questions? Not that that required significant expertise, but.
I'm like weirdly getting tripped up by the stars. I mean, I know what this is, but.
Well, because I want to distinguish column vectors from row vectors. I want to keep in mind what I'm using the object for. And even more importantly, later on in the talk, I'm going to introduce changes of bases. And the way the group of changes of bases acts on this vector space and this vector space is different. And it causes issues if you get confused. So I just need some way to distinguish this thing from this thing. It's, of course, if you want to allow yourself to take transpose, the same, but then I want to allow arbitrary change of bases.
Another notational question. So you wrote beta of V up there. And so that looks like you're thinking of beta as a linear transformation.
So V is a column vector in B.
Right.
And beta is a row vector.
Right.
And this is this row vector eating this column vector and giving me a number.
Could I as well have written V of beta?
V is living in the vector space B. Beta lives in the vector space B star.
Okay, and so you think of the starred spaces as being linear maps and the non-starred spaces as being
Yeah,
vectors.
so if V is a vector space, V star, by definition, is the space of linear maps from V to our ground field.
Okay, thanks.
So they really are two different objects, yeah.
I think I just missed something. What is that word when it's A tensor B star, it equals?
There's, space. Space of.
Oh, okay, just space.
Space of linear maps from B to A.
Oh, okay.
Other questions? Okay, so now I want to talk about tensors. So let A tensor B tensor C. Oh, yeah, and all my vector spaces are finite dimensional in this talk, and that implies that V star is canonically isomorphic to V. It's not quite true in infinite dimensions. So this will be, by definition, the space of trilinear maps, A star cross B star cross C star to our ground field. And again, if A is in A, B is in B, C is in C, let's let A tensor B tensor C denotes the trilinear map alpha comma beta comma gamma maps to alpha eats A, beta eats B, gamma eats C, and I multiply those three numbers, I get a number. And we say this is a tell me if I'm writing too far down. Oh, that's too low already? Okay. I will just go to the other board. No worries. I need high-heeled shoes or something. There's all this beautiful board space that I'm not quite reaching. And then there's this prohibited board space. Okay, so yeah, we say A tensor B tensor C has rank 1. And I hope you'll believe me that the cost of evaluating a trilinear map, if it has rank 1, is much cheaper than the cost of evaluating a random trilinear map. And more generally, the rank of T, so T in A tensor B tensor C, the rank of T is the smallest r such that T is the sum of R rank 1 tensors. And so we will be using tensor rank as a measure of complexity. In Olga Holz's talk, she may relate it to other notions of complexity like arithmetic circuits. And so for those of you coming from a complexity theory background, this is a legitimate complexity measure. I'm not going to give a proof of that right now. Okay, so an important class of examples is let A be I'm going to use script A, a finite dimensional algebra. So by that, I just mean a vector space with a multiplication map. And this has a structure tensor Oh, I should have said over here that this is also, for example, the space of bilinear maps from A star cross B star to the vector space C. And we have a bunch of other interpretations of this, of an element of that space. So just as over here, a linear map is also a bilinear form, over here, a trilinear map is a bilinear map taking values in a vector space rather than a number. So, okay, yeah?
Is there a reason, so like there's this asymmetry with the stars that's like for the matrices you have A star cross B, but for the tensors.
Well, I could, so I could let A tensor B be the space of bilinear forms, bilinear maps, A star cross B star to our ground field. But I wanted to start with linear maps because that's somehow more elementary. Maybe I think of it as, I knew what a linear map was before bilinear form, but maybe that's just my own ignorance. All right, so given a finite dimensional algebra, we get a structure tensor. Maybe I'll write it T sub A. So it eats, no, I want it, yeah, T sub A is a bilinear map. It eats two elements of the algebra and spits out their product. And so as a trilinear form, this something that eats, this is the things that eat elements of A. This is the thing that eats elements of A, and then we think of it as spitting out an element of A. And well, maybe the most important subexample, special case, is the algebra of n by n matrices. So, oh, I should say, rank T, and I want to write it not like that, but I'm going to write R of T as notation for the rank. So, since this is so important, this tensor, I'm going to give it its own name. Matrix multiplication tensor. So if we think of it as a bilinear map that eats a matrix, eats a second matrix, and spits out a third matrix, sorry, ran out of board, the naive expression, we do row column operations. So if this is a matrix alpha, this is a matrix beta, and this is a matrix Z, it's summation from, say, I, j, k equals 1 to n, alpha I, j, well, you do row column, row beta, j, k, and then it'll spit out C, K, I. If I write it as a trilinear form, I would eat an element of the dual space, and then it would be look a little nicer. It would be alpha ij tensor, beta jk tensor, gamma ki, and then it looks a lot nicer.
Sorry, what's like alpha ji? Is that like a?
This is So alpha is an n by n matrix. Alpha ij is the coordinate of the ijth entry. So alpha 1, 2 is the matrix that looks like that. But I'm thinking of this as a vector in a vector space. Is that? You're not happy?
It's a matrix with entry in the ij.
Yes. So this eats like alpha 1, 2 of a matrix A would just spit out A1, 2, the number in the 1, 2 slot. So this is, I'm really thinking of this as something that eats a matrix and spits out that entry of the matrix. But I can represent it this way.
I asked the question, I didn't raise my hand, but I'm
Oh,
happy.
sorry, he looked really unhappy.
No, sorry, yeah, I realize you're other people.
I think we're unhappy because you're using a different subscript superscript notation. It's just alpha sub ij is a more common notation, but that's maybe the only reason why people are.
Well, so I began my career in differential geometry, and there was this guy Einstein, and he's most famous for coming up with this way of writing down indices with implicit summation. He also made some contributions to physics, I'm told. So anyway, I'm sort of scarred by my childhood.
So it's covariant in one, but contravariant in the other?
Well, this is why I like this better, because then it has the same co or contravariance in all three. So this one eats 3 matrices and spits out a number. Nice exercise is that number it spits out is the trace of the triple matrix product.
Is this a good time to ask what is co or contravariance?
This is not a subject for this lecture.
Okay.
If somebody's asking that, that means they have too much expertise to be in the audience right now.
Maybe one comment. Maybe it's helpful to think of a trilinear form. Gets 3 matrices like ABC, multiplies them and takes the trace.
Isn't that what I just said a second ago?
Well, you use this one.
Okay.
Okay, you have your notation. Not all people may be so familiar with it.
Okay.
May help.
So anyway, this expression implies that the rank of this tensor, there are n cubed terms here, right? Because I'm summing ijk, is at most n cubed. And in fact, the standard way we multiply 2 by 2 matrices uses on the order of n cubed arithmetic operations. And then so this algorithm has been around for a long time. Yeah?
Yeah, sorry, one more notational question. So I'm tripped up by the fact that the I is a superscript on alpha, but a subscript on Z. Like, if I'm thinking, like...
Yeah, let's ignore it. Let me put them all down, and then... Okay?
Yeah, okay.
Okay, I didn't want to cause psychological problems. Well, if I do cause psychological problems, I'd rather have it be over something interesting than this.
Okay, thanks.
Okay, so 1968, Strawson, or maybe it was 1967, set out to prove that this algorithm, which has been around for ages, is the best possible. And how are we going to do that? That sounds difficult. So let's be more modest. Let's try and prove it's best possible for 2 by 2 matrices. But still, how are you going to prove an algorithm is best possible for 2 by 2 matrices? Well, let's work over the finite field with 2 elements. And then you could actually write down every possible arithmetic circuit or algorithm for multiplying 2 by 2 matrices over F2. And what he discovered, of course, which is why we're here, is that, much to his surprise, you can actually do better. And this standard algorithm, this expression star, is not optimal. In particular, the rank of 2 by 2 matrix multiplication is at most 7. He wrote down an explicit, well, he first wrote it down over F2 and then noticed it lists to the integers, an explicit rank 7 expression. And then, of course, once you know that, it opens the question, how much better can one do? So that prompted this definition of the exponent of matrix multiplication. Omega defined to be the infimum, and this infimum is important, over tau, such that the rank of matrix multiplication grows like into the tau. And then, probably sometime, I don't know when, there's this astounding conjecture that everybody cites and nobody takes credit or blame for. That this exponent is 2, which says that as your matrices grow in size, it becomes almost as easy to multiply them as it is to add them. Right. So, by the way, this 1968 Strawson discovery, had they chatted with algebraic geometers in 1906, they could have predicted this result for reasons I'll maybe get to later in the talk. So by 1970, Winograd, I hope I have my history correct, said in fact that this is correct. This is optimal for 2 by 2 matrix multiplication. But there was a lot of work, and I'm not going to name all the names, but you go to Peter Bergeiser's lecture, and so Strawson, in fact, in this language, showed that omega is at most 2.81, and then like by 1988, it got down to 2.38 or so. And I want to talk about the first bit of work here. I'm going to skip all the other stuff that came afterwards, but the first one is quite interesting to me. This was in 1980 or so. Dario Bini and collaborators said, what about if I multiply 2 matrices, but I insist this entry is 0. So let's call this M2 red for reduced. So naive algorithm is rank, says that the rank is at most 6, and the question is, what about equality? And so he was using state-of-the-art computer technology of 1978 or 79, whatever it was, and he was trying to find a rank 5 decomposition. And he was using a search method, like alternating these squares or some standard search method. And he was having a problem because he would get, his search algorithm would start getting close to a rank 5 decomposition, but every time it did, the coefficients would blow up. And I actually met him, and he told me this story, and he got very emotional about it. He was telling me he could not sleep at night. It was interfering with his personal life. But then he said one night in the middle of the night he woke up, and he'd been looking for the mistake in his code. He'd been looking, and he realized there was nothing wrong with his code. And the reason is that matrix rank, unlike tensor rank, is not semi-continuous. So matrix rank, oh gosh, I hope I didn't break anything. Right. So if I have a curve of matrices, so depending on a parameter, and the matrix rank of MT is R for all t greater than 0. So let's say a smooth curve. It doesn't really matter. Oh, continuous, to be precise. Then the rank of M0, well, it could drop, but it can't go up. But in fact, this 2 by 2 reduced matrix multiplication, it is the limit of tensors of rank 5, but it itself has rank 6. And to explain this phenomena, he defined the border rank the smallest r such that T is a limit of rank R tensors. And the theorem, which is your homework, is, it's not a joke. It is assigned, and you will have working group. You could work on it in a team if necessary. That
I was appreciating.
is at most 5. And in fact, it equals 5, but that was done later. Right.
Sorry. How are you defining a curve of matrices? What is that parameter doing?
Right. So for example, I have t squared t cubed plus 7t, 5 minus 4t, and t plus 2. This is a curve of 2 by 2 matrices. For each value t, I get a 2 by 2 matrix.
Are those polynomial, or can that just be arbitrary?
They will be polynomials in this talk, but the definition is arbitrary smooth curve. Yeah, so that arbitrary continuous curve is allowed, but we'll be restricting to analytic curves, but that's no loss of generality, but that's a theorem.
What is the bad behavior happens even for polynomials?
Or the good behavior.
Basic question. You seem to be relating the rank of matrix multiplication to the complexity of an algorithm for computing matrix product. What is the relationship between those two?
Yeah, that's Olga Holtz's talk.
Okay.
So I promise, but I believe I convinced everyone in the room that the rank of a matrix is the measure of complexity of computing the matrix vector product. And then I asked you to believe that analogously, the tensor rank is a measure of the complexity of computing the associated bilinear map. I did not prove it.
And maybe it's getting ahead of ourselves, but is the border rank going to be relevant to complexity?
That is a theorem, yes. So yeah, thank you. This is exactly the next thing I wanted to say. Theorem. This is Bini. Also captures the complexity, i.e., to be precise, the exponent is equal to also the infimum over tau of the border rank of this matrix multiplication tensor. So this thing is less than or equal to the rank, but asymptotically, they capture the same growth in complexity. And one could be more precise about that, but I won't in this thing. And so, like, I guess from 1980 to 2006 or so, it was open question, this border rank of 2 by 2 matrix multiplication. So it was known to be 6 or 7. So now that's done, 7-1. But embarrassingly, perhaps, what about the border rank of 3 by 3 matrix multiplication? Well, let's see. So for rank, already in the 70s, it was known to be less than or equal to 23, and it's at most 19 by one of the many experts in the audience. And for 3 by 3 border rank, it's known that 17 is less than or equal to the border rank of 3 by 3 matrix multiplication. It is less than or equal to 20. This is due to Smirnov. And this is due to Connor, who will talk about this on Friday, Harper, and me.
Question?
Yes?
In your definition of omega, do you have a logarithm somewhere?
I forgot the rest. Order of n to the tau. I wrote it properly the first time, and then I got sloppy. Sorry about that. It's the same thing I wrote before with a bar here.
Okay.
But this is a theorem, the other was a definition. Okay. So, so when I first heard about this astounding conjecture, I thought it was kind of ridiculous conjecture, so I thought we should try to disprove it. In any case, as a mathematician, if you're not working both sides trying to prove and disprove something at the same time, you're not working properly. So so how to prove lower bounds? So,
excuse me, question?
Yeah.
So just to clarify, because it seemed like for the regular sort of rank of the multiplication tensor, it seems like the decomposition just gives you the algorithm, more or less?
Yes.
And so for border rank, it's sort of less clear that decomposition?
Well, what you do is you pay a price, and you convert your border rank algorithm to a rank algorithm. Now, that price for your matrix of size, say, 10 by 10, could be quite expensive. But the increase in price from going from a 10 by 10 matrix to a 1,000 by 1,000 matrix, it's basically the same price. So by the time you're at 1,000 by 1,000, as far as the growth is concerned, it's as if you had a ranked decomposition from the start.
You don't care at all about the rate of these coefficients blowing up or things like that?
Well, are you asking, for the purposes of this talk, am I going to discuss it, or about whether?
Downstream, if you want to get an algorithm. It sounds bad somehow, but maybe.
Yes, so I agree that is an important topic, but it's not the topic of this talk. We will be talking about that this fall. But this talk is just sort of some upper bounds and lower bounds in complexity. Other questions? Okay, so yeah, so what about, so there's this fantastic book on complexity by Aurora and Barak. Oh, I hope I spelled the name correctly. Is that correct? Yeah. Good. Yeah, so they have this great book that I've learned a lot from, and I highly recommend it. And they have a chapter, chapter 14. It's called Circuit Lower Bounds, Complexity Theory's Waterloo. And there's a reason for that. So, okay, so what I'm saying is if we want to prove lower bounds, we maybe should start out a little modest and just be happy to prove anything. So, so let's go back to the matrix case and see what we can do. So I'm going to assume the matrix rank is our measure of complexity for our matrix or for our bilinear map. And so, so recall a matrix has rank at most R if and only if all of its size R plus 1 minors. So the determinants of all size R plus 1 submatrices are 0. This is your second homework problem. One direction is very easy, but the other one is you have to think about a little bit. And so the naive thing, so the first border rank lower bounds is, well, is a retreat to linear algebra. So here I'm going to do something really silly. Let's look at our space of tensors. And so I want to know the subset of this space which consists of tensors of border rank at most R. So I want to test. You hand me a tensor, and I want to test to see if its border rank is at most R. And here's the stupidest possible thing we could do. I draw some parentheses. This is a vector space, so I could view this as a space of matrices. So we immediately get 3 types of equations. So we could look at T, let me say A, think of it as a map from A dual to B tensor C, TB is a map from B dual to A tensor C. TC is a map from C dual to A tensor B. And the claim is the border rank of T is greater than or equal to the max of the ranks of these three linear maps. So good news. Explicit, easy to compute, polynomials. Bad, can at best prove that the border rank of T is greater than or equal to the maximum of these three dimensions. And let's see. So if I draw a picture, let's say this is the set of, let's say, M tensors of rank at most 1. This has dimension roughly 3 times m, because I get to pick a vector here, vector here, vector here. It's not quite true. It's 3m minus 2 because of the scalar. But my ambient space has dimension m cubed. So if I have a tensor of rank 2 or border rank 2, it's a sum of 2 of these. So I get to pick a point here and a point here. So this set has dimension something like twice times 3m minus 2 plus 1, because I get to pick a point. I pick 2 points, and then I pick a point on the line. And in general, r of t less than or equal to r, this set has dimension roughly r times, let me just ignore all the other details, roughly like 3mr. And for that to get to m cubed, we see that a random or general T has border rank around m squared over 2 or 3. I always forget, whatever it is. But it's order of m squared. Well, m squared. I'm going to forget the constant. So here and here, this would be m. With those techniques, we're pretty far away from anything. And so we got to be a little bit smarter to do better. Oh, what time should I stop?
15 minutes or so, quarter past.
Those are 2 different numbers.
That clock is wrong.
OK, so by that clock, which is what I'm looking at, what time should I stop?
10:18, maybe?
OK, thank you. OK. So, right. So let's try a more sophisticated retreat to linear algebra. So if you think about what I did when drawing these parentheses, I took my space of tensors and I viewed it as a space of matrices. But we could be a little bit more sophisticated and look for linear maps that take my space of tensors to a space of matrices. So some big space of matrices. And then if the usual matrix rank the usual matrix rank of the matrix f of t is less than or equal to S for all t with rank 1, then if the border rank of some t tilde is at most r, then the usual matrix rank of f of t tilde has to be less than or equal to r times s. So we reduce from multilinear algebra to linear algebra. And your third homework problem this works. And there's an explicit example of vector spaces here that you can make it work for. And notice that this kind of thing, well, this sounds like a ridiculous idea because how would you ever find good vector spaces V and W? And that brings us to perhaps the most important part of this talk, is how are we going to prove these things, and how are we going to take advantage of the tools available to us. Now, the property of rank and border rank is independent of our choice of bases. So if I make a change of bases in each space, the border rank won't change. And so I have a group acting on my space, and I have a quantity that is invariant under the action of the group. And the idea is look for f respecting the group action. So let's let GLA be the changes of bases, the group of changes of bases, of basis in A, that is to say in coordinates, these are the A by A invertible matrices. And my group is the product of changes of bases in all three. So it's natural to look for these space of matrices here respecting that group action. That is to say that this, the group G, should also act here, and the map should commute with the two group actions. And this idea has led to, okay, so I guess, yeah, so I guess I should say in 1983, the first non-classical bound got like R, so T now will always be an M tensor. So if we're doing matrix multiplication, n is n squared, R of T greater than or equal to 3/2 M. He basically used a variant of this idea, this retreat to linear algebra, but it was phrased very differently. But it's almost equivalent to some of these.
Question, if you say non-classical, you mean not just based on linear algebra?
No, not just based on this.
Non-classicals. Oh, okay.
Well, I mean, first bound that's better than the local dimension.
Okay,
so this is an M tensor. Roughly, it's not entirely true, I know,
not
but
only what is here, but also you said more sophisticated repeat, but it's also different from that. It's also different from the more sophisticated repeat.
Right, so this is, well, so in hindsight, Strawson's bound can be viewed as a special case of this, actually a weak version of a special case of that. But of course, he phrased it differently. But again, it had this group invariance going for it. But now,
Should that be 3 halves m or m squared?
no, so where?
Oh, when you said the RTs at least.
Yeah, so if matrix multiplication is in Cn squared tensor, Cn squared tensor, Cn squared, so m equals n squared
Oh,
here.
thank you.
That's why I use 2 different letters, m and n. I'm taking full advantage of those 24 characters of the alphabet to distinguish. Okay, so this is great, and it led to like the state of the art is around, well, it's not so much better. It's like 2m minus log m with these methods. So this was like in the 2000s. So it took from, prehistoric times to 1983 to go from m to 3/2 m, and then it took another 40 years or 30 years to go from 3/2 m to 2m. And then in 2018, we got some bad news. In the computer science world, this was discovered by Efremenko, Garg, Oliveira, and Wigderson. But also in algebraic geometry, there's a group starting with Bernardi, Ranestad, going up to the Baczynski family. They're 2 different people that basically game over for this idea, almost over. So I just erased it, which is unfortunate, but we remember we were taking minors of matrices. So that has the advantage of being very explicit, but it has the even better advantage that one of the few polynomials we can compute efficiently is the determinant. And so the equations that we know of are equations we can compute efficiently. So it's kind of double win, right? They're explicit and efficient. And so let me be precise about the game over. Cannot prove border rank of t greater than or equal to 6m with these methods. And actually, recently, Baczynski and I conjecture that that 6 is actually a 2, but that's current research. So the only polynomials we know how to compute are determinants, and there's a theorem that says those are not going to do the job for us. So we have to give, yeah?
Sorry, I realized I got lost on something super basic, which is like, if the rank is m, which is n squared, I guess, what's the runtime of matrix multiplication? Like for each factor, doesn't it take n squared time for
this
that
is
one factor?
lower bounds.
Yeah.
So I'm proving that you cannot do better than that. I'm proving that it's going to cost you at least 3/2 n squared rank 1 tensors, and a rank 1 tensor has a cost, some fixed cost to evaluate, which for the purposes of this talk, which is not morally correct, but I'm lazy, I'm just thinking of a rank 1 tensor as cost 1, but of course that's not true. It's cost like m.
Yeah, that's what I'm confused
Yeah,
about.
so you can multiply everything by m if you're talking about cost, but I'm talking about tensor rank, which is a measure of cost, and to convert it to the proper measure of cost, it's actually a factor of 3. I think is the
Like
theorem.
you need, somehow, like, if you actually want to convert it, you need like a factorization where the factors are also like sparse or something.
No, nothing like that. It's assuming if you calculate all scalar multiplications as unit cost, or if you bound the size of your scalars, then there's a fixed conversion factor. And I'm saying if you count a scalar multiplication, no matter what the scalar is, as cost 1, then that factor is some number between 3 and 6, but that's across the board, and I'm just going to sweep that under the rug. So I'm interested in the growth in complexity. So if it's a constant conversion rate, then we can do that at the end
I
of
think what I'm confused about is like for a matrix, the runtime to multiply it by it isn't just the rank, it's the rank times.
I completely agree, but that times is a fixed number that we know. And we have an upper bound. And even if you want to do like bounded precision or whatever, then there's some other fixed number that's bigger that takes into account, how long your number is. But I'm not dealing with any of that in this lecture.
I guess additions are...
There will be lectures dealing with that, though.
I guess additions are free? Is that...
Well, actually, it's not quite that. It's that additions will not add to the growth. So again, there's this fact. So the number of additions is bounded above by the number of multiplications. So that's why I went from 3 to 6. So there's a 3 for something else, and there's a 2 because I forgot additions. So that's where the 6 comes from. So these costs are there, but they're constant. So when I'm studying these theorems, I could have different numbers, but the shift would be by constant shift. Yeah.
Which I guess is not obvious. Like it could have been that the rank decomposition has like n terms in one of the terms, right? But it's not the case, you're saying.
I'm saying that a rank 1 tensor, there's a fixed cost for computing the associated bilinear map.
Oh, I see.
And whatever that cost is, cost C, you take whatever numbers I'm writing on the board and you multiply them by C. But the important thing is that C is a constant. Okay? There was a question over here first. Sorry.
Yeah, just clarifying, I think you said this already, but by these linear algebra methods, you mean like these flattening maps?
These flattening maps, no, specifically determinants.
Okay, just determinants. It's not like all low-degree polynomials. There might be
Determinants. Determinants is what is our downfall. Well, it's what has saved us so far. It's what all lower bounds that I know of use determinants. And we were told in 2018 by 2 different groups of people who didn't even talk with each other that much. I mean, I talked with both of them, that we're not going to get much further.
I was going to say, a way to think about what you were saying here about like the tensor rank of an n by n multiplication is once you show a bound on it, it doesn't actually tell you that for dimension m matrices it's fast. Rather, it gives you an upper bound for much, much larger matrices. And that's how you can subsume these other things as constants.
Well, there's two different ways to play the game, and I'd rather not get into that now. I think Jim Demel's going to talk about that. No, or Olga. Well, somebody may talk about it. If not, I'll be delighted to talk about it with you, but not right now since I'm almost out of time. And I wanted to say one more thing because otherwise I'd be ending this whole lecture on a very depressing note. So we have to give up on these general lower bound results for tensors for the moment, because the only polynomials we can compute are determinants, and those are almost exhausted their use. So the idea, though, is, at least in complexity of matrix multiplication, we don't really want to compute lower bound for all tensors. We want one tensor. And even if in real life, you're usually handed very special tensors that you want to bound in complexity theory. Not in engineering, but this is complexity theory. So what we do, and what the newest developments have been, is to not, what's it, like this natural proofs barrier kind of thing. To get around this sort of natural proofs barrier, we work with bounds tailored to our particular tensor, like matrix multiplication tensor. And then there's another group that shows up. So here we have the group of changes of bases that leaves tensor rank and border rank invariant, but there's also a subgroup of that group that will not change our tensor, the symmetry group of our tensor. And in my next talk, I will explain how one might be able to exploit that symmetry to prove kind of boutique lower bounds for your particular tensor that is perhaps not subject to this bad news. Thank you.
Thank you very much for this enthusiastic talk, J.M. We had many questions, but maybe there are more comments.
So I have a comment. So you mean, of course, you are concentrating on multiplication tensor, but first of all, in most of the tensors you take have a generic rank, and most of them border rank is equals to generic rank. So what you are interested in very special tensors.
That's what I just said a moment ago. This is a computer science lecture. Not in engineering. In engineering, the world hands you the tensor, and you have to deal with it. But we're doing complexity theory. We pick the tensor, but it's an important tensor. It governs all operations of linear algebra, and we want to know how difficult is linear algebra. Can we do linear algebra more efficiently, both theoretically and practically? That's the theme of this semester, as far as I understand. And
we are given the matrix multiplication tensor. We don't have a choice.
Yeah.
So what are the complexity theoretic implications of proving better lower bounds? So if I increase the constant, what are the implications?
So that goes back to the Waterloo issue. You see, we need to be content with any lower bounds we can get. And just, the fact is, lower bounds did not move for 30 years. And then now they're starting to move again. And I agree, ultimately, it's not, the final word is not going to happen until somebody can go beyond. But, for all we know, the border rank of matrix multiplication is 4n squared. And then, we have a huge party.
So if you went above linear and M here, that would be evidence that we probably can't do better than, we probably can't reach order n squared.
That would be a certificate that we cannot.
For
if I could do m to n to the 2 plus epsilon,
yeah,
that would be a certificate that the exponent of matrix multiplication is greater than 2 plus epsilon, and bounded away from 2 for some fixed epsilon, yeah.
So you mean m to the 1 plus m to the 1 plus epsilon?
Or m, yeah, I was saying n.
Okay, okay, sorry.
Yeah, m to the 1 plus point, yeah.
So just to make it clear, to understand right that this proof barrier only applies to methods that work for any tensor.
Exactly.
So okay, yeah.
Exactly.
That's why it's
That's why I say it's like this natural proofs business, kind of, morally speaking, if you're familiar with that.
Is there any proof barriers that apply to subsets of tensors maybe that are also large maybe? Or
I am working on something there's no theorem like that I know of, but there is work being done about that. And I'd be happy to talk about it offline.
Okay. So I think it's time for the coffee break. Thanks a lot.
I just want to say there's a stack of paper outside if anybody needs paper or wants to do it.